Okay, I will start recording. Okay, so howdy everyone, and thank you for joining our ARMA Texas A&M R&D series. And today our topic is weirdly shaped hydraulic fractures from petals to pancakes. And our speaker is Dr. Egor Dontsov, who is a chief scientist at ResFrac Corporation, where he develops a fracture front tracking algorithm to address the problem of mesh dependence. Previously, Egor worked at W.D. von Gonten Laboratories, and as an assistant professor at University of Houston, he has over 50 scientific peer-reviewed publications, most of which are in the area of hydraulic fracture and proton transport modeling. And with that, Dr. Dontsov, you can start your presentation.
All right. So thank you very much for the introduction, and thanks for having me here. Thanks for the invitation. So I'd like to start with one of my favorite quotes from Benjamin Franklin, saying an investment in knowledge pays the best interest, right? And so what it means is that you always need to try to learn something new, something exciting, something useful. And I guess that's one of the reasons why we have this series, right? So you guys are eager to learn new things and hope that they'll be useful to you in the future. But and another reason why I like this this quote is because it not only applies to your major if you're a student, like it's not only about learning how to solve differential equations, right? If you're a mathematician or know how to drill wells, it's also about things in life, right? And you don't overlook these things. So what I find over the last several years, that many people, especially the young ones, and when I was younger, just overlook these things, that you also need to learn things, how to buy a car, how to deal with your finances, how to meet people, and so on. So all how to present, how to write. I mean, these are also all important skills, and don't overlook this. It's also your knowledge. It's also going to pay your interest in the long term. So that's how I want to start. But now let's start with our business, right? So you're here, I believe, because you want to learn about hydraulic fracturing, and I hope I won't disappoint you. And I have this very catchy title about weirdly shaped hydraulic fractures, because when I found it out about this, this thing that I'm going to present, it's actually, they were very weird and it was hard to explain. And actually, I should date it back, this work back to my University of Houston days. And at the time I was looking for funding, and I invited Xiaowei Wang. Xiaowei Wang, for those who don't know, he now retired, but he worked at Schlumberger. So he was one of the, he was leading the group who was developing hydraulic fraction simulator at Schlumberger. And we had conversation in my office, and he said, well, we have a problem. And the problem is that we don't understand this weird shape of hydraulic fractures, that sometimes we pump a stage and all fractures grow nicely and symmetrically. But sometimes we pump a stage, say, with several fractures, and then we have a situation when some fractures go left, some fractures go right, and we don't know why, and we don't know how to control it. And so that was the issue. It was back in 2016 or 17, something like that. But anyway, at that time, I didn't know how to answer that, but still, this problem was burning in the back of my head, and so eventually I figured it out, and so that's what I'm going to present. Oops, let's start. So first, well, since I'm from ResFrac, I have to say a few words about ResFrac. It's going to be one slide, and then we're going to move on. So ResFrac is a company founded by Mark McClure and Charles, right? And this is the first commercial product, right, in hydraulic fraction, which combines fracture propagation, reservoir flow, and geomechanics simulation, all under one simulator, right? So we have, as you can see here, the module for fracture propagation, multiple fracs, multiple stages, multiple wells, with all the proton transport and a lot of other physics. And then you can seamlessly simulate reservoir flow, and then geomechanics. Geomechanics could be like pure elastic induced stresses if you do production, or thermoelastic stresses if you're interested in geothermal applications. And And one of the key things is it provides robust numerical solution, and it's actually designed just for application, mostly for field applications. But actually here I want to say just a few words about this robust numerical solution. Is very important. Look, I work in both academia and industry, okay? And I wrote both simulators for academia and industry, and it's a very big difference, even though it's like, oh, I mean, I write this hydraulic fraction simulator in academia. Is it the same as an industry, or is it better, is it worse? But you need to understand they're very, very different, because they serve very different goals. Because in academia, your goal is to write a paper, right? So write a simulator, and so what you do, you want to run several cases. You run several cases, you have pretty pictures like this, you publish a paper, you're good, right? You're good to go. And in industry, it's very different, right? Because your clients use your code, it has to be absolutely robust. It has to work all the time. It has to converge all the time. So it has to be bulletproof. And bringing an academic simulator to be bulletproof is very, very far from trivial. Okay, so that's why this phrase robust numerical solution is really, really important, and don't think that it is trivial. Okay. All right, so I also want to say a few words about previously recorded presentations, which you can find online. So one was from office hours, ResFrac office hours. Again, you can sign up for those if you want to on our webpage, or just email one of us. I did it actually back, I think, in January, February, but the date is June 8th, but maybe that's when it was posted. It was actually, I was talking about very similar topic of this hydraulic fracture shape, but this current talk is better, right? Because it's actually, it has some more information and more, some additional information that has never been presented before. So stay tuned. And second one is about the thing I actually implemented in ResFrac. It's about fracture front tracking algorithm. And again, this talk was part of the ARMA warm-up series, and it's posted on YouTube. So again, if you're interested, you can, here's the link, you can watch it. And so this is basically more about, the things that I'm working on ResFrac. And I think it's very interesting to my point of view, but it's a little bit more technical, right? So less educational. And so that's why I chose like this topic, because it's more educational. But in a nutshell, so this is about the algorithm which you allow to track the fracture front gradually to have like partially filled elements, and you can account for layers, geomechanical layers, which are thinner than the fracture element size. Like for this example, you have this fracture shape, and this color shows the compressive stress. You have high stress layer here, and then even higher stress barrier, but very thin, and then lower and lower stress. And this is your element size. So it's not triangle, it's rectangle, it's square actually. So it's like this. This is your element size. I don't know if you can see my mouse. And so your layer can be much smaller than the element size, and you can still account for it. So this, I think it's very exciting, and it's also very new. But again, it has more technical details. So again, if you're interested, please watch this this video, and then you can always send me questions using this email address. Right, now let's go to math, but this talk is going to be a combination of math and pictures and for understanding, and so so the first thing I want to talk about is the radial hydraulic fracture. Right? It's a very simple geometry, because in my view, a lot of learnings can be done by just looking at simple geometries, because you can easily analyze. There's just fewer parameters, right? And so in the radial hydraulic fracture, we have no layers, so we inject somewhere in the middle. We have radial symmetry, and so we have some governing equations here shown here on the left bottom. So we have the continuity equation, we have Carter's-Leakoff here, we have a fluid flow equation. Here's the mu prime is just 12 mu fluid viscosity. So this is fluid flow. We have elasticity equation to ensure that our rock surrounding the fracture, because you open the fracture, is in equilibrium, and the propagation condition, right? So which relates the fracture width to material parameters such as fracture toughness, which here is like scaled with some numbers. So K1C material toughness, like a strength of the rock, if you want, and the modulus, right? So these are well-known equations. I don't know if you haven't seen this. I mean, don't worry about it. So it's okay. But maybe at some point, if you'll be investigating more about hydraulic fracture, you will learn more about these equations. But again, so the basic physics is that you have the volume balance, you inject, and this volume goes either inside the fracture or leaks into the formation. And then you have fluid flow inside, so you have the pressure gradient along, basically because you have viscous flow. you have elasticity around the rock, and you have some criterion of propagation. This is a fairly complex system of equations, so let's try to think how we can easily analyze it. And one way of doing this is just saying, okay, let's take out all these derivatives, integrals, just look at the order of magnitude. Say your fracture opening has some scale, and think about whether it's like 1 millimeter, 1 meter, and so on. Just like its characteristic dimension or size of fracture. So again, we take all the derivatives out, so we have some equations right here. Or say from here, right, we say the width should be actually characteristic width W star equals some toughness times over the modulus times square root of the radius, right? Again, just order of magnitude. Okay, and the reason we do this is because this is complex to solve precisely mathematically. This is very easy to solve precisely mathematically, right? Because it's just algebraic equations. And here we have 6 equations, 4 unknowns, right? I mean, you can count number of equations and unknowns. So we cannot solve it. So instead what we do, we say, what if we take 2 equations out of it, okay? And here, let's focus on so-called viscosity storage solution. So we say, what if we kick out toughness and kick out leak-off? Okay, and if we do that, then we can solve with 4 equations, 4 unknowns. Now we know how radius depends on time, how characteristic width depends on time, and pressure depends on time. So we know how they scale with viscosity, how we scale with injection rate, with modulus, and so on. For instance, now you can answer the question saying, what if we say we have some solution? Now, what if we pump for twice as long? How much longer the fracture is going to be? What if we do the same, but we change injection rate or viscosity? How solution is going to change? And so you can do this without solving anything, right? And if you want to do it precisely, then I mean, you can get precise answer, but based on scaling, you just get the main dependence on the main problem parameters, and you don't get these numbers in front of it. Okay. And then you can do the same, but for a toughness storage. Now you can say, okay, what if my viscosity is small, say I inject a gas? Now you remove this fluid flow equation. Again, no leak-off, remove leak-off. Now again, you have solution based on scaling for the radius, width, and pressure. And now you get so-called K-vertex or toughness solution, which is, most people know a Sneddon solution. Okay. And again, just without solving any differential equation, just back on the envelope calculation, now you can know the radius, the width, the pressure, how they roughly behave. So that's very powerful. And finally, if you want to understand the transition, say between toughness and viscosity, now you make those equal, say radius or width or pressures. And now you can find the parameter, dimensionless parameter, which governs the dominance of one of another. Like, think about this. You have your radial fracture, you have some certain parameters. How would you know if toughness is large enough? Or how would you know if viscosity is large enough so that viscosity dominates the response, right? But this dimensionless group allows you to understand it. I'm going to show you just in a second how exactly to do it. But again, even just without calculations, you just look at this and you can say, okay, if my viscosity is 0, right, then this dimensionless time is much larger than 1. It means that we are in a toughness dominated case, means the viscosity is small, toughness is large. And vice versa, if tau much less than 1, it means that toughness is small, nearly 0, and viscosity is large. Okay. And again, you may still think that it's very theoretical and so on, but again, just bear with me. It's going to be, really it's going to show very interesting results. But the key out of this is this parameter. We know what physics dominates the response. Okay, that's the reason. And again, another way you can visualize it is you can just plot the radius for one solution, for Sneddon solution, for toughness dominated solution, and for viscosity dominated solution. Say on a log plot, they're going to have different slopes. They're going to intersect somewhere. And so the true solution, if you do it numerically, is going to be like a black line. And so what you're really doing when you try to understand what controls this transition is you try to find the intersection point. So that's pretty much it. So here's the final result. Okay, so after omitting some mass, right? So you can rigorously show that for radial fracture, there are actually only 2 dimensionless parameters which govern the solution. And so these are, these two parameters shown here, tau and phi. So previously I just showed you how to derive this tau, but again, you can do it more rigorously based on equations. But what it really shows is that there have 4 limiting cases when various physics dominates the response, okay? So storage viscosity, it means our toughness is really, really small relative to viscosity. So when you pump, this viscous fluid, everything is determined by viscosity. And there is no leak off, right? So this is storage. Storage toughness means, again, there is no leak off. So no leak off means everything stays within the fracture, right? Whatever you inject volume, this volume stays within the fracture. And no viscosity means that toughness really dominates how the fracture propagates. And then we have 2 similar cases, but with large viscosity. And so the way to read this is the following. So you have your material parameters, viscosity, modulus, leak of coefficient, injection rate, toughness. You compute these 2 numbers. And now if you are in here, these 2 numbers, tau and phi, if you're in here, it means that your toughness is very, very small. And so the whole solution is dominated by viscosity. And it also means that your leak off is very small, means everything that you inject stays within the fracture. On the other hand, if you end up somewhere here in purple zone, say K tilde, it means that your viscosity is pretty much negligible. It really doesn't matter if you change viscosity, your solution is going to be the same. It's all fracture toughness, all the rock properties which determine the fracture size and fracture behavior. And then it also means that the leak off is very large, because this is like one of the leak off regimes. What it means is that most of the fluid which you inject actually leaks into the porous formation, and so fracture volume is much less than whatever volume you pump. Okay, so that's what this means. And so if you're in the middle, it means you're somewhere in the middle. It means your leak off is strong but not strong enough. So maybe like 50% of fluid stays within the fracture, 50% leaks, and then both viscosity and toughness are important, right? And in field applications, we are in most cases actually somewhere in the middle. So that's how you read it. And then if you're interested in terms of, another thing is that for all these 4 cases, there are exact or semi-analytical solutions. So and that's why they're written here, but it's useless to remember them. You just need to know that they exist, right? They exist. Now here's an example how you can use it. Okay, just one potential example, because one obvious example is that, say you're developing a new hydraulic fraction simulator, right? And now you want to know that whatever you coded is actually correct and accurate. And so one way of using this is to set up a set of parameters in which you are somewhere here, say in M regime, and now you run your simulator against analytical solution for these parameters, and now you see or check if they're the same or not. But if you're in the M regime, you check the viscosity, your flow term, on limitation of flow terms, but you don't check the toughness. And then you say, okay, now you do another set of parameters so that you're in toughness regime. And now you check that your propagation condition is implemented accurately. And then these 2 are without leak off, and then you pick one of those 2, again, find the parameters so that you're somewhere here. And then you test whether your leak off implementation is correct or not, right? So this is one way of doing this. Another way of using this diagram, and it's been used, as far as at least several times, is to design laboratory experiments, right? For instance, let's take some field values for Young's modulus, toughness, injection rate, injection time, and leak off, and let's compute these 2 numbers, right? You just basically plug it in the numbers, and so you get a point, right? So you're somewhere here. Again, and I use the numbers such that you are, somewhere in the middle. And now you say, okay, what if I change viscosity, right? And now if you change viscosity, now you jump somewhere here. Now you can see that if you use, 100 centipoise viscosity, now and for these injection parameters, now your toughness is not important anymore, right? And now you say, now I want to design a laboratory experiment and say, now I take the real rock with the same parameters, right? Whatever shell or whatever you want to do, use sandstone, same toughness, same modulus, same leak off. I use the same water, but now because my rock is small, now I adjust injection rate and time, right? Because in the lab, they do like foot by foot experiments, right? You cannot inject for 1 hour at 18 barrels a minute, and so you adjust the rate. And what happens if you do that? Now you ended up here. Again, so you try to simulate your fracture behavior somewhere here relative to your parametric space, where viscosity is important. But when you scale it this way, now you're right here, right? It means that this is not a proper scaling of your field parameters or characteristic field parameters to lab. And so instead, what you should do is to go back up here is to increase viscosity, right? And instead of using 1.5 CP viscosity, I don't know, use 10, 15, 100, 1,000 centipoise so that you are back up here. So this is this one way how you can use this in parametric space for designing laboratory experiments. But that's now is a slide, I guess, which justifies the title of this work, because so far it's been all fundamental, if you wish, theoretical, even equations and so on. But really, these equations allow us to understand and to describe this really weird phenomenon, which was observed, in numerical simulations, and which was bothering even this, as I said, it all started with Xiao Wang, who observed but couldn't explain it. This dates back in 2020, but actually I did it a few years before that when I was working for Van Gonten Labs, and so we used the internal simulator called external simulator Fracoptima to run several cases for multiple fractures as a function of this parametric map. So imagine you have a well, horizontal well, and now you propagate simultaneously, say 5 or 10 fractures, and use limited entry, which means that you have uniform flow distribution between the fractures. And let's look at the fracture geometry as a function of your location inside parametric space. Again, the coloring is the same, right? So blue is viscosity, and no leak of. Red is toughness, and again, no leak of, and these are 2 leak of regimes. And so here's an example of simulation also. So you have a horizontal well bore, you have 10 vertical fractures, which are closely spaced. And now you set up the parameters. Again, I don't need to specify exact parameters, toughness, leak of, whatever, but you set it up such that you are here in the blue zone, storage viscosity. And you can see all these 10 fracs are basically like pancakes, right? So that's why, in title, see pancakes, they're all pretty much the same. You have some variability of fracture fronts. So there are like 10 of those fractures, and if you can count all of them, they're very closely spaced. And no matter what parameters I choose, smaller, larger, as soon as they're closely spaced, and as soon as viscosity dominates, they're nearly identical. And now if you do the same, but for toughness-dominated fractures, means when you have very low viscosity, relatively speaking, but have a lot of toughness, now you start having this shape. So that's what I call petals, right? So each individual fracture forms like a petal. So the fractures really want to avoid each other because they're competing for space, and this is like effect of stress shadow, and so they develop very complicated shape. And moreover, this solution is unstable. So you run it several times, you get slightly different results, because stable solution would be radial fracture, because again we have here no layers, no gravity, nothing. So it's supposed to, if you inject in a single fracture, you would have a single radial circular fracture. But here instead we have this very unstable solution. And the way to understand this, and by the way, there is no mathematical proof, and then if you're willing to work on it, this would be great. But just to understand why is this the case is, if viscosity dominates, right, what it means is that your fluid flow really determines the fracture shape, and there is no resistance of rock at all. And so the fluid flow, because you have you inject here, it really wants to be symmetric. It wants to be radially symmetric, because if you propagate asymmetrically, you introduce essentially more resistance, right? So you want to minimize fluid flow resistance, and if you want to minimize it, it becomes nearly in a radial shape. If you're in a toughness domination, on the other hand, it's really viscosity is not important. What's really important is your fracture energy, right? So fracture energy essentially is related to your fracture toughness, and then modulus is fracture toughness squared divided by modulus, and times the surface area. So here we want to minimize total surface area, right? Because that's what fractures can control, and then they can grow anyway. If you're in toughness regime, it doesn't matter. You can grow up, you can go down, left or right. It's the same effort, and so that's why they really want to minimize the overlap. They want to minimize the overall surface area of all this, system of fractures. And so that's why we can see, this petal thing. Again, this you may think about just speculation. Again, there's no mathematical proof for that, but that's, this roughly what's going on. And then again, you add Likov, conceptually things don't change much. It's still somewhat similar. I mean, you still see some wiggles and fractures here and there, but they mostly overlap and mostly symmetrical. And once you have a lot of Likov and still toughness domination, you still have this weird, shape of fractures. Again, they grow very unstably. And then you have intermediate cases, right? So again, you gradually transition from here, from right to left. I mean, you start seeing, kind of more symmetry, more overlap, but still very, very, weird, weird shapes. And again, I want to confirm that here there are no layers, no propant. You have no, multi-physics, some complex things. It's just you have 10 fractures propagating simultaneously from horizontal well. You have uniform spacing. You have uniform flow distribution. Again, no layers, nothing. So it's just the mechanics of this problem, right? Just this instability. And this is actually in the simulator called Fracoptima, right? And some questions say, oh, well, maybe you have a mistake in the code, right? Or maybe you have, I don't know, maybe it's code dependent. But hey, I mean, I did the same thing in ResFrac, right? So Fracoptima and ResFrac was written by two different people. They use different programming language. They use different numerical schemes. Everything is different, except the mechanics, the basic equation that they're using underneath. And well, I didn't use exactly the same parameters between these two, but I was roughly here. I was trying to capture the viscosity dominated regime here and toughness dominated regime here. And the pictures on the left here basically are stretch, just to better see the fractures are stretch. This is a real picture, right? The real spacing between fractures. And here I just stretch them 10x so that you can see the structures better. And again, you can see they're conceptually very, very similar. And so here in toughness regime, your fractures are all kind of try to occupy their own segment, right? And they don't like to be overlapped. And it is the same. I mean, you can argue that the number of petals is different. Well, yes, but again, these are different codes. And at least in Fracoptima, if you run it several times, you get quantitatively different results, even though qualitatively they're the same. So again, I would say these results are very, very similar conceptually. And for viscosity dominated as well, right? You can see there is tons of overlap and nearly like this looks like stacked pancakes, right? So it's not about the numerical code. It's not about how you code these equations, how you solve this equation, and it's not like an artifact of a given quadratic fraction simulator. It's physics, right? It's the way it is, and that's what we have to deal with and understand. And one question that pops up is, well, okay, well you have all these things now, you can understand it how fractures grow, but what would be the potential application? And well, I see one at this point. Maybe there are more. But here's the thing, right? So right now, one very popular way of diagnosing fracture propagations use fiber optics well, right? So for those who don't know, so we have, say, your treatment well right here, and say you pump the stage here. So in this case, 6 fractures. And now you have several wells, offset wells, and you put a fiber optic cable there. And by this, in these wells, you record you record stretch. You record stretch along along the well as a function of time, and that's how it looks like. So you have the stretch as a function of time, right? Horizontal is time, horizontal axis is time, vertical is stretch, and so you can see the fracture approaching here. You can see the first fracture hit, second fracture hit, and so on. And then you shut in the stage, and that's fracture closing. And then you can start analyzing this data, start to do history matching, right? So you want to understand what's going on. You want to match fracture lengths, fracture arrivals, and the number of crossings as well. And that's where this can come into play, because look, if you have viscosity domination, right, or strong viscosity domination, if you put an observation well through here, then all of these 5 or whatever how many fractures you have will likely arrive at about the same time. right? And that's not what we see here in the field, right? We have one fracture arrival, second, third, fourth. It's not like they're all the same, right? They're not arriving at the same time. On the other hand, if you have toughness domination here, you can imagine any offset well here. And you see the fractures don't like to overlap, which means in this case, you see only one fracture. At least, again, if you have no layers, of course, right? And if you have uniform flux distribution, there are a lot of ifs, but in this limit, you would see only one. But we see many, right? So it probably means that we are somewhere in the middle. So none of those is exactly dominates. So both toughness and viscosity are important. Or maybe there are some other effects which also determine these things. But I guess this is at least one application how this can be used to try to history match this data and try to history match the fracture morphology. So this was about radial fracture, and that was, again, I probably didn't mention something that I did before back in 2017, 18, and it was published 2020. But then you might argue, well, but we have layers, we have prop point, we have other things, and what do we do about it? And so one thing is that I did quite recently is try to extend it for PKN or constant height hydraulic fractures, because arguably, I mean, your fracture shape is somewhere in between this constant height PKN fracture and radial, right? So if you have strong barriers, strong layers, so you're close to PKN. If you have no layers or weak layers, then it's more like a radial. So your true solution is probably somewhere in between. Okay, and so for those who don't know, the PKN and constant height hydraulic fracture is a very old model. It was developed back in 60s, 70s. So assume a constant height fracture. This is like a half fracture. So inject here. It's a symmetrical problem. We have very strong barrier so that the fracture propagates horizontally and have constant height. And we have in each cross section we have elliptical fracture opening, and the length is supposed to be assumed to be much longer than the height. It's kind of long, and thin rectangle. And so in this case, the problem is still one-dimensional, just like radial. So radial fracture is one-dimensional problem because we use axial symmetry. Here, we know the solution in the vertical cross section, and so essentially average out of the vertical direction, and then we have one-dimensional formulation. So let me show you just a few equations, and then again we're going to continue with pictures. So just again, for those who like equations, so just the way to get the equations for PKN geometries to write them down first for planar fracture. Yeah, I'm not going to go into details, just give it, just outline. And then what you say, you use all the assumptions, right? You say, okay, now fracture doesn't go outside of the main layer. You do elliptical cross section, and then we have horizontal flow. And so basically you plug it in, and then you average over vertical direction, then you get some, simplified one-dimensional equations. Okay, I mean, you can go, there are many publications on this topic. You can go through this on your own if you want. But one interesting thing is about elasticity equation, because the elasticity equation is such that far away from the fracture tip, it is so-called local elasticity is used. That is, the fluid pressure inside the fracture is linearly proportional to the fracture width. So it's just like, it's really local, means if you open fracture a little bit on say somewhere here on the right side of the fracture, it's not going to affect pressure somewhere in the middle. So it's local. And so far away from the tip, it is local, but close to the fracture tip, it is non-local, and actually it resembles the plane strain or KGD model, right? So well, as you know, the KGD model applies when your fracture length is much shorter than fracture height. And next to the fracture tip, that's exactly the case, right? Your disk characteristic length is when it's smaller than height, then we essentially go back to elasticity equation for KGD fracture. But the reason why I'm telling you this is because actually we have two options for the solution. My goal here, I mean, as you can probably guess from the radial fracture, is I want to have some sort of parametric space, right? I want to see when toughness dominates, when viscosity dominates, when leak-off is important, when it is not important. And then I want to see how it all applies to these multiple fractures, right? And so, and here I want to choose the right approach, how to construct the solution. And so there are two ways. One is to use this local elasticity. So essentially you capture the bulk of the fracture, but ignore effects near the tip. And another is more accurate solution. And so here I'm showing results of one of the numerical simulations, which I did back in 2016, my University of Houston days, which compares the widths along the x-axis for this PKN fracture for various parameters. And so here, the solid line is fully planar simulator. In this case, it was implicit level set algorithm or ILSA, but it can be anything. And then the dashed black line is the one which kind of more accurate, but uses non-local elasticity. And the dashed colored line, the one that like simpler, but use local elasticity. And as you can see, they are not bad, especially for lower toughness. They're not bad. I mean, but near the tip, they introduce some error. But if you worry about just the fracture lengths, kind of just global fracture dimensions, lengths and widths and so on, then this would be an appropriate choice. I don't want to go into the difference between these two, but that's again, you can look at this publication if you want to learn more. But what I want to say here is that, well, you can potentially use a solution with more superior accuracy, like this dashed black line, but it's a bit more complex, right? And so instead, I want to use a simpler solution for analysis, which here is like a dashed red line. For extreme cases, it doesn't capture well this behavior near the fracture tip, but it's roughly captures the width and roughly captures the length, so it's good enough. Okay, and so if you do the same analysis as for the radial fracture, so we can outline. Again, I didn't repeat it, all the scaling and so on, but you can write down the formulation, remove all the derivatives, and then try to do this algebraic equation and find the parameters which determine the result. But you can find, again, two-dimensional parameters. Again, they look horrible, but it is what it is. And these two-dimensional parameters determine whether toughness is important, whether viscosity is important, or whether leak-off is important or not. And these are all these, again, all these numbers in mass. I mean, they're not that relevant, but these basic equations of these dashed lines define, the boundaries on this plot. But important thing is that now we know for PKN fracture, we know what parameters we should choose to ensure that viscosity dominates or when toughness dominates. So, and that's something that wasn't known before. Now it is available. And this, by the way, is going to be all this parametric space and derivation is going to be in the book chapter, which hopefully will appear in 2022. But I mean, things get delayed all the time and so on. So sooner or later, it's going to be available. And again, you can have, just like for radial fracture, there's just a whole bunch of solutions. You can analytical solutions which give you the solution in for limited cases. So you can try, and again, you can, again, if you develop in your own simulator, you can again, if you want to test whether this propagation condition is right, you set the parameters so that you're in the K regime. If you want to test your fluid flow equation, you set the parameters so that you're in M regime, and then you do your testing. Okay, but we are here to look at graphics, right? We're here to learn about how all these can be important for multiple fractures, right? Because that's the ultimate goal, ultimate connection. Because again, as a theory, all these equations are fun, for some of us at least. But at the end of the day, we need to make sure that we use it, right? So, or find some applications. And so what I did it just a week before this talk, because I really wanted to do it for a long time, but really didn't have time. And now you gave me this opportunity, right? So, and as you probably know or will know that if you have a deadline, so you always meet it, right? So it's good to give yourself a deadline. Otherwise, things never get done. Anyway, so basically what I did, so once I know the parametric space, once I know these dimensionless parameters which determine where I am, I just set up several cases in ResFrac and try to understand how fracture geometry or morphology changes as a function of parameters, right? So I used 3 sets of parameters. I didn't use leak-off because I didn't see any conceptual difference before for radial fracture for results with or without leak-off. So I just used toughness and viscosity. So one case was in toughness dominated regime, one case in viscosity dominated regime, and one was in the middle. And as you can see, conceptually, the results are very, very similar to what we saw in the radial fracture. And this is again, so you have horizontal well, you have PKN geometry in the sense that you have strong barriers above and below the injection well, and you have normal layers, you have everything homogeneous, perforation friction is high, you have uniform flow distribution and so on. And so if toughness dominates, then you see that again, fractures tend to avoid each other and create quite complex shapes, right? And again, you can see here, say 2 fractures go left, 3 fractures go right. So this fracture is short and wide, and these are more skinny and longer fractures. And this is again, these are the same solution. This is original spacing, and this here is just stretch a view along this well by 10x, so that we can see each individual fracture. And then we increase viscosity, and now you see fractures are more symmetric. They're still unstable, asymmetric, but they're more, again, they're more symmetric. And if you think about arrival of the fiber optic at the fiber optic well, the observation well, they would probably arrive at about the same time, or maybe with some delay, but we would have several crossings. And if you increase viscosity really high, then you start seeing, again, just for the radial case, nearly identical fractures. Some things going on here near the tip, but they're pretty much identical. And again, and the good thing about this math, which I showed you, that now you can quantify where you are. And again, if you do history matching, now you can look at this parameter. This is tau, which dimensionless time, which determines where you are. Some things are known, some things are unknown. For instance, your model is pretty much known. You know it pretty well with good accuracy. Injection rate is known, injection time is known. Viscosity, again, is something that typically is quite well known, but it depends. But you see, there's the first power of mu, so even if you off by a factor of 2 or 3, you're not going to change things much. But your toughness here has power of 5, so if you're off in your toughness guess by factor of 2, 3, 4, 5, then you can jump here between 2 regimes very easily, or if your fracture height changes, right? So that's how you use it. And now here I want to show, like, this slide is about stress shadow, because now obviously all these things are the function of stress shadow, the stress interaction between the fractures. That's what drives it. And I don't know if you noted, but everywhere I was talking about small spacing, right? So it's closely spaced fractures, closely spaced radial fractures, closely spaced PKN fractures. But how close is close? Okay, so let's try to find it out. And so here's one of the figures from a paper by Ken Wu and John Olson back in 2015, which shows how stress decays as a function of distance, or normalized distance divided by the fracture height, right? So it's now you can see that if you open the fracture and you go, say, distance 1, so 1 fracture height, now your induced stress is more than halfly reduced, right? So you reduce it by more than a half. And now if you're 2 fracture heights away, now you almost don't see the induced stress. Means there is almost no stress shadow between the fractures, right? So it's all about the distance divided by the fracture height, or spacing between the fractures divided by fracture height. And so here's what I did. Again, ran several cases in ResFrac in a toughness regime, so very large toughness, small viscosity. The original case is here. So spacing over height ratio is 1/8, and I have 5 fractures, right? But so spacing is 1/8, right? So it's closely spaced fractures. That's what I mean is this ratio is very small. And the same for radial fractures, but for the radial, you not divide by height, but divide by the radius. And then I ran several cases and tried to alter the spacing over height ratio, and for the same parameter, so just basically increase spacing. And so as you can see now, you start seeing less overlap, and then less overlap, and now eventually, once your spacing is twice as much as the height, as you can see from previous slide, there's almost no stress shadow, right? No interaction between the fracs, and so all the fracs are identical, right? So again, just to confirm that this is, all this thing is all due to stress shadow, stress interaction between the fractures. And you can do the same exercise for the transition between toughness and viscosity. And again, this is my original case. Spacing over height is 1/8, and now as you try to change the spacing, again, you eventually converge to identical fractures, right? And then as you try to squeeze more and more fracs within a stage, now they start avoiding each other. And in the viscosity regime, right, if you have very high viscosity, then really doesn't matter, right? So I mean, matters a little bit, right? You can see, like, for this case, like few fracs a little longer than others, they're not identical, and here have some wiggles here and there. But if you look in the bulk, right, in the bulk fractures, then they're pretty much identical. All right, so, and this brings me to conclusion, right? Time flies when you're having fun. So that's my last slide. So in summary, so let me summarize what I hope you learned today. So the first thing is that the scaling can be used to make quick estimates of the solution, right? So you don't always need to solve these complex equations, integral, differential, whatever equations, just to make quick estimates of the solution. You can do a lot of things just by using pen and paper. And you can do it, it's not going to be precise, but it's going to give you an idea of what to do in your, say, numerical simulations. And if you're talking about solutions or fracture geometries with simple geometries, by simple, I mean, essentially your governing equations are one-dimensional. So you have radial symmetry, you have plane strain or KGD model, or you have PKN fracture. You have 4 limiting solutions. You have storage viscosity solution, where you have essentially large viscosity, no leak of storage toughness. You have large toughness, no leak of, and the same too with leak of viscosity, leak of toughness. That's when you have a lot of leak of. And all these parametric spaces are quite useful and can be used, for instance, to benchmark numerical codes or design laboratory experiments. Or, as you saw, there's a good application for multiple fractures as well, right? And so for multiple fractures, what we found is that it's quite universal conclusion, right? No matter fracture geometry, as you can see here, if your viscosity dominates, you have a limited entry, right? So you have uniform or equal distribution of fluid in each fracture, then the fractures are nearly identical, apart from a few wiggles near the fracture front, no matter whether you have radial symmetry or PKN geometry. On the other hand, if you crank up the toughness or reduce viscosity, then you start seeing these weirdly shaped hydraulic fractures, right? So you can they also form petals if you have radial symmetry, or I don't know how to call the shape, right? But they want to avoid each other, right? And the way to control it is you can change, because you cannot change toughness, right? You cannot change modulus, but you can change viscosity of your injection fluid, you can change rate, you can change spacing, you can change number of fractures. So this is something that this effect can be controlled, and so you can understand whether you are here on the right or here on the left. And finally, I just want to say that mathematical analysis of this stability problem is still not done. It's very complicated. I tried to think about it, but I couldn't quickly come up with a solution. So if you feel you want to do it, I'll be very happy for you. All right, so thank you so much for your attention, and I'm looking forward to answer your questions.
Thank you very much, Dr. Dontsov. Yeah, please write your questions in the chat or unmute yourself and ask it. I think we have some questions in the chat already. So the question is, how realistic is the solution if we ignore the leak off? Okay, that's a good question, right? I mean, of course, we do have leak off in reality, right? And I have nothing against leak off, but you see, first of all, in shells, what can happen is that your leak off is relatively small, right? So it's not about neglecting the leak off, right? It's a question, where are we here in parametric map? You can still have some leak off, but it can be relatively small, right? And so you still will be within these regimes. But another reason why I didn't do leak off for this particular case is because I did it previously for radial fracture. So if I go back here, I did it previously for radial fracture, and it wasn't very exciting, right? I mean, conceptually, it is the same. So here, these cases, right, this dot and this dot, they have quite high leak off, right? And so conceptually, in fracture shapes are pretty much the same. So for this case, I wasn't ignoring leak off, and it didn't affect the results. So that's why I decided not to include leak off into PKN models. Okay, so the second question, I guess, I mean, I can read it. The second question is, does estimation of stress shadow in Wu and Olsen indicates that limited entry perforation design with at least 1,000-1,500 PSI loss
may overcome stress shadowing effects at small spacing and lead to more uniform stimulation for slick water job. Okay, so so here's the thing, right? Again, to answer this question, so it's not just this. Okay, so you have limited entry, right? So which promotes a uniform flow between the fractures, and now you have small spacing, right? But if you really want to overcome stress shadow effects, you must have quite large viscosity, and then if you have large viscosity, that's when you overcome the factor of stress shadowing. And the same applies for PKN or for radial fractures, right? So if you have large viscosity, you are here. Have small viscosity, you are here. But then there is actually a very interesting thing which I didn't talk about, because do you really want to overcome the effect of stress shadow? Really? And so at some point I ran several cases for radial geometry, and the only thing that I was changing was viscosity, right? And I was plotting the total surface area as a function of viscosity, because you can think about, you want to overcome the effect of stress shadowing to have more surface area, right? So I mean, this visually has more surface area than this, right? But the reality that the only thing that you change is viscosity, it isn't. Because once you start increasing viscosity too high, your fractures become shorter and fatter. So your width becomes higher and length becomes shorter. And because of that, even though it's visual, it looks like more beneficial, you actually have less surface area for this case than in this case. And what I found, at least for this particular case, that if you're roughly in the middle, that's when you have, like basically I plotted the total surface area as a function of viscosity. And I found if you're roughly in the middle, this corresponds to the peak of total surface area. And so really, I mean, you need to think about exactly what you want to achieve with your design, like overcome stress shadow or have more surface area, more production, right? So these are different questions. All right, so we have another question. Without running a simulation, if I use your quick estimate, I found that the fracture is in the viscosity dominated zone. Shall I expect that the reservoir will have the maximum fractured zone? I'm not sure. Can you please clarify what do you mean by maximum fractured zone? I mean, do you want to increase the surface area or something else? Because again,
Igor, can you hear me?
Yes.
Yeah. Yes. My question is, will I expect a maximum fractured or stimulated zone with the maximum fracture surface? Because it looks like if any fracture falls in the blue zone, I shouldn't be happy, because I know there's a lot of fracture surface, so that I have a maybe higher production rate.
Right. Okay. Well, I think that's exactly what I was trying to answer the previous one, because if you let's think about that fracture surface area is a proxy for production, right? Then the total surface area of this case, if you're in blue zone, is actually smaller than total surface area if you are here, because if you increase viscosity too much, then the fractures become shorter in length. Right, think about this, the outer diameter of this thing, say 300 feet, and the outer diameter of this is 100 feet. Even though there's a lot of overlap, then the total surface area, is higher here. But that's not just this, because, say if it really depends, right? Because say you have layers, some layers are more productive than others, and now you really want to have, say, a lot of identical fractures near the wellbore for whatever reason, then this can be more productive. Okay, it really depends. And then if you start adding layers, things can become very different. Okay, and so I think there is no universal answer, because every situation can be different, because once you start adding layers. But overall, if you look at the total surface area, then if you are in the middle, that gives you the highest total surface area, like overall.
I got it. Thank you.
Mm-hmm. Okay, so I have a next question. It seems that fracture geometries are planar for all the cases. Does it mean that the fracture planes are predefined? Whether the non-planar fracture geometry will affect the results? That's an excellent question. And actually, when I was publishing this paper, this 2020, one of the reviewers asked exactly the same. And so what we did is we ran a similar series of simulation, but for non-planar cases. And here by non-planar, I mean they are vertical non-planar. So basically, if you look from the top, they can curve, but they cannot create like a ball, right? So basically, they just curve in one direction. That's what Fracoptima, at least at that time, that Fracoptima allowed to do. And we did that, and conceptually, we didn't see much of the effect. So we still saw, but basically, it was, well, actually, you know what? I can open this paper right now and show some. Here you go. Right, I don't know if you can see. So these are 10 fractures, and here you see a lot of curvature in the viscosity regime, and then a lot of curvature and toughness regime. And again, conceptually, the results are very similar. So, I mean, quantitatively, there could be some difference, of course, because you allow for a lot of curvature, but conceptually, it's not a stopping point for having very, very different behavior, right? And here's a 5 fracture case. Here's 10 fracture case, right? So you see they are all follow the same logic, if you wish. All right. So let's go back to this. Where's my Zoom? Okay. I lost my chat. Sorry. Did anybody ask another question?
Not at the moment.
It's not here. It's not here. Here's chat. There you go. Okay. And then answering to the first part of this question, that yes, these fracture geometries are planar, and the way I did it here in Fracoptima is just basically introduced very large stress contrast between between the minimum and maximum horizontal stress, and in ResFrac we just have an option to make it, to force them to be planar. So okay, any other questions? And then again, as I said, I mean, you can always, if you have any questions, you can always email me back. So at some point, I had my email right here, or you can search me on the web page. ResFrac.
Is there any other questions? Let's see. Well, if there are no more questions, then I would like to thank you, Dr. Dontsov, for accepting our invitation and for an excellent presentation. Yeah, and I think we can stop if you don't have any other questions.
Thank you very much. Have a good evening, everyone.